In this segment, we're going to look at another form of encryption called tweakable encryption. I'm going to motivate tweakable encryption using disk encryption as an application, and we'll see disk encryption as yet another application for deterministic encryption. So the disk encryption problem is that we want to encrypt sectors on disks. Say each sector is 4 kilobytes long. And the problem is that there's no space to expand. In other words, if the sector size is 4 kilobytes, the ciphertext size also has to be exactly 4 kilobytes because there's nowhere to write the extra bits if the ciphertext was bigger than the plaintext. And so our goal is basically to build a non-expanding encryption where the ciphertext size is identical, exactly equal to the plaintext size. So what does it mean that encryption can't expand? Well, technically we're saying basically the message space is equal to the ciphertext space. So the message space would be 4 kilobyte messages, and the ciphertext space would be also 4 kilobyte messages. In this case, clearly we have to use deterministic encryption because if encryption was randomized, there would be no place to store the randomness. And similarly, we have no room for integrity because we can't expand the ciphertext and add any integrity bits. So the most we can achieve is deterministic CPA security. And that's going to be our goal. Now, it turns out there's a really simple lemma to prove that basically says that if you give me a deterministically CPA secure cipher where the message space is equal to the ciphertext space, so no expansion, then in fact the cipher is a PRP. So really all we're saying here is if we want no expansion at all, our only option for encrypting is what we called construction number 2 in the previous segment. Namely, we have to encrypt using a PRP. So let's look at how we might encrypt using a PRP. Well, we take our disk and we break it into sectors. And now if we encrypted every sector using a PRP under the same key, we kind of run into our standard problem with deterministic encryption. Namely, if sector 1 and sector 3 happen to have the same plaintext, then the encrypted sector 1 would be equal to the encrypted sector 3, and the attacker would learn that the corresponding plaintexts are the same. Now, this actually is a real problem. For example, if some of your sectors are empty, they're all set to 0, then in fact the encrypted sectors would be identical, and as a result the attacker would know exactly which sectors on your disk are empty and which sectors are not. So this is actually quite problematic, and the question is, can we do any better? And so the answer is yes, and the first idea that comes to mind is, well, why don't we use a different key for every sector? So you can see sector number 1 gets encrypted with K1, sector number 2 gets encrypted with K2, and so on and so forth. So now even if the content of sector number 1 is equal to sector number 3, the ciphertext of sector 1 and sector 3 will be different because they're encrypted under different keys. So this actually avoids the leakage that we talked about before, although I do want to point out that there's still a little bit of leakage in this mode. For example, if the user happened to change 1 bit in sector 1, and then that sector gets encrypted into a different ciphertext, so this will be garbled all completely because this is a pseudo-random permutation, the sector will be, even if 1 bit of the plaintext changes, the sector will be just mapped to a completely new random output. However, if the user then undoes the change and reverts back to the original sector, then the encrypted sector will revert back to its original state, and the attacker can tell that a change was made and then reverted. So there's still a little bit of information leakage, but that type of information leakage, there's really nothing we can do without really sacrificing performance. So we're just going to ignore that and deem that acceptable. So the next question is, now you realize our disks are actually getting pretty big and there are lots of sectors, so this would mean that we're generating lots and lots of keys here. But of course we don't have to store all these keys, we can simply generate these keys using a pseudo-random function. So the way this would work is we would have a master key, which we would call K, and then the sector number, which I'm going to denote by T, is going to be encrypted using the master key, and the result of that encryption would be the particular sector key, which I'll denote by K sub T. Now the reason this is secure is again because the PRF is indistinguishable from a random function, which means that basically if we apply a random function to these sector numbers 1, 2, 3, 4 up to L, they basically get mapped to completely random elements in the key space, and as a result we're encrypting every sector using a new random independent key. So this is a fine construction. However, again, for every sector we would have to apply this PRF. And so the natural question is, can we do even better? And it turns out we can, and this introduces this concept of a tweakable block cipher, where really what we want is basically to have one master key, and we want this one master key to derive many PRPs. So we said one way to do that is simply encrypt the key K using the PRP number. But as we'll see, there's a more efficient way to do that. Now this PRP number is actually what's called a tweak, and that introduces this concept of a tweakable block cipher. So in a tweakable block cipher, the encryption and decryption algorithm basically, as usual, take a key as input, they take a tweak as input. This capital T is what's called the tweak space, and of course they take the data as input and the output data in the set X. The property is that for every tweak in the tweak space and a random key, basically if we fix the key in the tweak, then we end up with an invertible function, a one-to-one function on the set X. And because the key is random, the function is in fact indistinguishable from random. In other words, for every setting of the tweak, we basically get a PRP, an independent PRP from X to X. And as I said, the application for this is now we're going to use the sector number as the tweak, and as a result, every sector is going to get its own independent PRP. So let me very, very quickly just define more precisely what is a secure tweakable block cipher. So as we said, there's a tweak space, there's a key, a tweak space, and an input space X, and as usual, we define our two experiments. Here in experiment 1, what's going to happen is we're going to choose a truly random set of permutations. So not just one permutation, we're going to choose as many permutations as there are tweaks. So you notice this is why we raised this to the size of the tweak space. If the size of the tweak space is 5, this says that we're choosing 5 random permutations on the set X. And in the other case, basically, we're just going to choose a random key, and we're going to define our set of permutations as the ones defined by the tweaks in the tweak space. And now the adversary basically gets to submit a tweak and an X, and he gets to see the value of the permutation defined by the tweak T1 evaluated at the point X1. And he gets to see this again and again. Again, he gets to see the value of the permutation defined by the tweak T2 evaluated at the point X2. And so on and so forth. And then his goal is to say whether he interacted with truly random permutations or pseudo-random permutations. And if he can't do it, we say that this tweakable block cipher is secure. So the difference from a regular block cipher is in a regular block cipher you only get to interact with one permutation, and then your goal is to tell whether you're interacting with a pseudo-random permutation or a truly random permutation. Here you get to interact with T random permutations, and again your goal is to tell whether the T random permutations are truly random or pseudo-random. So as usual, if you can't distinguish if the adversary behaves the same in both experiments, we say that this PRP is a secure tweakable PRP. Okay, very good. So let's look at some examples. So we already looked at the trivial example. In the trivial example, what we do, we're going to assume that the key space is equal to the input space. So this PRP really acts on X times X to X. So think of AES, for example, where the key space is 128 bits, the data space is 128 bits, and of course the output is 128 bits. And then the way that we define the tweakable block cipher, again there's a key, a tweak, and data as input, is basically we encrypt the tweak using our master key, and then we encrypt the data using the resulting random key. Now you realize that if we wanted to encrypt n blocks with this tweakable block cipher, this would require 2 n evaluations of the block cipher. N evaluations to encrypt the given tweaks, and then n more evaluations to encrypt the actual given data. So I want to show you a nice example that shows that we can actually do better. This is called the XDS construction. It's actually originally based on a mode called XEX due to Roggeway. And it works as follows. So suppose you give me a regular block cipher that operates on n-bit blocks. So not a tweakable block cipher, just a regular block cipher. We're going to define a tweakable block cipher. So again, this tweakable block cipher is going to take 2 keys as input. The tweak space, for convenience, which you're going to see in just a minute, we're going to assume this tweak space is made up of 2 values, T and I. T is going to be some tweak value, which we'll see in a minute, and I is going to be some index. And then X is going to be an n-bit string, which we're going to apply the tweakable block cipher to. So the way XDS works is as follows. The first thing we're going to do is we're going to encrypt the left half of the tweak, namely T, using the key K2, and we're going to call the result N. So now what we're going to do is we're going to XOR the message M with some padding function applied to this value N that we just derived at the index I. And this padding function is extremely fast. We can pretty much ignore it in the running time. The next thing we do is we're going to encrypt using the key K2. And then we're going to XOR again using the same pad. So we're going to XOR again using the pad of n applied to I, and the result is going to be the ciphertext, which we'll denote by C. Okay, so again, as I said, the function p is some very, very simple function. It's just a multiplication in a finite field, which I'm not going to explain here. Very, very fast. So the running time is really dominated by the running time of the block cipher E. And that's it. That's XTS. And the nice thing about this construction is now if we wanted to encrypt n plus 1 blocks, all we do is we compute the value n once, and then for the indices 1, 2, 3, 4, basically we just need to evaluate the PRPE once per block. So we would need to encrypt n blocks using the tweaks t, 1, t, 2, t, 3, t, 4, and so on. We would just need n plus 1 evaluations of the block cipher E. So it's twice as fast as the trivial construction. So I want you to stare for just a minute at this XTS construction. So my question to you is it really necessary to encrypt the tweak before using it? That is the following construction a secure tweakable PRP? So you can see in this construction the tweak is used directly as input to the padding function for the XOR, and my question to you is if we did that, would that be a secure tweakable PRP? Now let me remind you again that this is the key, this is the tweak, and this is the data. I hope everybody said that this is the correct answer. Basically, if we set the data to be pt, 1, then when we XOR it with the corresponding tweak, which is also pt, 1, we're going to get here 0. And so what's going to get encrypted is actually 0. So whatever that comes out to be, let's say that's some value C0. And then the actual output is just going to be C0 XOR PT1. Now when we do the same thing with PT2, we're going to get C0 XOR PT2. And when we XOR these two things together, we just get PT1 XOR PT2. So the fact that this is true means that an attacker can simply query the challenger at this tweak and this data, this tweak and that data, and then just compute the XOR of the two responses and compare to the XOR of the appropriate padding values. And if the equality holds, we're interacting with a pseudo-random function. Otherwise, we're interacting with a truly random function. So this would allow the attacker to defeat this construction with advantage 1. So just to summarize, the way XTS is used for disk encryption, what we do is we look at sector number T and we break it into blocks, 16-byte blocks, and then block number 1 gets encrypted with a tweak T1. Block number 2 gets encrypted with a tweak T2, and so on and so forth. And so every block gets its own PRP, and the whole sector as a result is encrypted using a collection of PRPs. Now you notice this is a block level PRP, it's not a sector level PRP. So in fact, it's not true that each sector gets encrypted with its own PRP, it's just each block gets encrypted with its own PRP. The distinction between a sector and a block is somewhat artificial, and this XTS mode actually provides deterministic CPA encryption at the block level, at the 16-byte level. That's the goal. And this mode actually is fairly popular in disk encryption products. I just wrote a couple of examples here that actually support XTS. So I wanted you to know that this, in fact, is how disk encryption is commonly done in practice. So to summarize, tweakable encryption is a useful concept to know when you need many independent PRPs, all derived from a single key. One important thing to remember is, in fact, the trivial construction is not the most efficient. There are constructions like XTS are actually more efficient, where you can kind of reuse encryptions from one tweak to get many encryptions for many different tweaks. And so those are the better ways to use them. Both the trivial construction and the XTS construction are what are called narrow block constructions. Namely, they provide a tweakable block ciphers for a 16-byte block. But as we said, we looked at the EME construction in the last segment, which provided a PRP for much larger blocks. And in fact, EME is a tweakable mode of operation. So if you need PRPs for larger blocks or tweakable PRPs for larger blocks, then you would just use EME. But you notice there in EME, you had to apply the block cipher twice per input block. And as a result, it's twice as slow as XTS and is not very often used. So that's what I wanted to say about tweakable encryption. And in the next segment, we'll talk about format preserving encryption.